Very good morning to you all present here. So today the topic of this talk is materials and processes. I will be talking mainly on selection and some kind of introduction to these materials and processes. Alloy design and thermomechanical processing, which happens to be the main topic of these 4-day deliberations. So materials, definitely when we talk about alloy compositions, then this talks about materials. And when we talk about processes, thermomechanical processing is one of the subsets of various processes available. So it is a very important topic to for any person or engineers or scientists to know what is the selection process by which we design a product and bring the idea to a product. So materials and process selection becomes so important before we do any alloy design or any processing. Because we should know what materials are required and what processes for those particular materials are suited to reach to a component of a product. And the left side, you are able to see this. See the different kinds of properties in the form of charts. So these are the availability of properties about the materials, and we also know that we have databases on processes. Just suppose if this person, he thinks of an idea to produce a car with a given function, and then he would like to have the materials as well as the processes by which his idea can be translated into a product. So what we will do through this talk is try to understand that within a framework that how he will be guided under the framework to select materials and processes. So before we go to that, we will have some small introduction about materials and processes. If you look at the evolution of engineering materials, then from prehistoric times to the present, here if you see the importance of different materials that change. Initially there were copper, gold, bronze, iron, like that, and then the importance of metals increased, and finally the importance of polymers, elastomers, and composites, ceramics, they increased. So all these things happened because in the prehistoric times, when we did not have technological advancements, at that time we had easily available naturally occurring composites, glasses, or polymers. But later on, based on the requirement of the society, metal were developed, and we were basically using large amount of metallic alloys. So here you can see the large number of alloys, steels, light alloys, super alloys, titanium alloys, they got developed in these times. Now, later on, what happened that we went to large amount of technological advancements, and that led to the new kind of applications. Just a moment. Now, if we look at the processes, the materials basically, that how the materials evolved through time, then you can see in the around 50,000 BC, we can say that the prehistoric times, we had basically ceramics, natural materials, metals, and with the passage of time, new materials developed, and finally, today, we have a large chunk of materials available with us for developing any product we want. So if we say in a nutshell that we have basically 3 different classes of materials available with us. And these are metals and alloys, which consist of steel, cast iron, aluminum, magnesium, zirconium, titanium, and copper alloys. And similarly, we have polymers where we can see polyesters, nylons, elastomers, isoprene. Many of the polymers are available in this. Then ceramics and glasses. Not only that, these main classes they also lead to a new class of material that is called composites. And these composites, if you see what they are. So, for example, uh, we know steel and tire cord. We use. So polymers and metals and alloys, if they can be mixed in certain proportion and in certain arrangement, they can lead to a composite. Similarly, carbon fiber reinforced plastics and glass fiber reinforced plastics, all these materials also can be termed as composites. And we also know the ceramics and aluminum alloy composites with the ceramics. These are metals and ceramic composites. So with this amount of materials available with us, we have the possibility of choosing different kinds of uh, different materials for different applications. Not only that, we have in addition to composites, we also have different kinds of new materials like metallic foams, lattices, uh, segmented structures, sandwiches. These we call hybrid materials. So what we can say that we today have a large amount of materials available with us with databases, and we need to choose materials from this large gamut of groups, and then also decide which material can be suited for which applications. So far as application is concerned, the materials can be divided in two major roles, like load-bearing materials, which we call structural materials. So in load-bearing materials, we basically deal with the property of material where it can bear the load. For example, in elastic modulus, the property we care for. Then yield strength, UTS, hardness, ductility, all those things. Thus, if materials corrode or wear, then also we can say that they basically degrade the capacity of the material to bear the load. So that can also be that those properties can also be taken care of for structural materials. And then there are functional materials. Functional materials we do not take care, do not get concerned on the mechanical load bearing capacity, but certain functional properties like optical, electrical, dielectrics, magnetic and thermal properties. If we look at how the properties determine the product behavior, then here you can see this is an aircraft, and if the modulus of the wings is low, it will bend like this. If the yield strength is not enough, there is a tendency of deformation. And if the fracture toughness is low, then in that case, there may be breakage, or if it is very dense, then it will sag like this. So to have an aircraft standing in this position, we have to have the properties which are required for such an applications. And then there are other properties like high temperature behavior, then thermal conductivity. You are able to see that the pictorial views, and they are good enough to explain to you that what it is for. Then magnetic properties, then electrical conductivity of the material, thermal expansion properties, and light absorption properties. So we can say that there are large number of properties with a large number of materials, And so we divide them as a class of material properties where we can define different class. I will not go into detail of this because video will be available with you later on. So economic class of economics of the materials, the general physical properties, mechanical properties, thermal properties, electrical and magnetic properties we just discussed. Then the main thing nowadays we are considering is of environmental interactions, how the material and material interact with the environment so that it doesn't deteriorate the environment and does not get deteriorated due to the environmental conditions. Then optical properties, production processes, how they can be produced. That is called ease of manufacture, how we can join them, what is the possibility of getting good finish, then formability and weldability, and then aesthetic definitely. All these materials, from raw materials to finished product, if you want to go, there are different processes like primary processing where we do casting, molding, deformation methods, powder metallurgical methods. Once we do this bulk primary processing, then we also need to go for secondary processing like machining of the material and then heat treatment to have the desired microstructure for the material so that it can be useful for the given applications. And then there are joining and surface treatments. We may choose of what kind of joining, what kind of surface treatment of the material is required. So having all these processes applied to the material, you get the finished product. Now, if a material is chosen and we have decided that what function it has to perform, for example, material we have chosen and function it has to perform, then we need to understand that what process, the shape and process are interrelated, what process and what shape we have to give, and using the process, what kind of structure and property of the material could be obtained. So from materials to the functional requirements, we need to be very careful on the shape. Definitely shape has to be determined as a geometric constraint for material for an application. Then process, shape, structure, property. These have to be taken care of for the function. So process determines the shape, process determines the structure, and process determines the property. So materials and processes are so important to decide what kind of function, to decide what would be the property of the material to perform a given function of the product. So in total, we can say that whether metals, ceramic or polymer, we have to take care of the composition and processing to reach to certain structures, and that will determine the property and performance of the product. Okay, with this, we will come to materials processing, why we do that. So we have a raw material, then the material has to go through a manufacturing cycle where we put the input is given as machines, tools, power, and labor we give. And in this manufacturing cycle, we get the product as well as some form of wastage. And what we do in this process, we add value to the material, and the process add values to the product, and this is obtained by various processes we call extraction, melting, then casting, deformation processing, powder processing. So all the processing we do with the raw materials, they are actually doing the value addition to the material for a product. And what we want to have from this value addition, faster production, better performance, and cheap. But nowadays we also have one new constraint that it should sustain. There has to be sustainability options. There is no option basically. It has to be sustainable in the future. so that the environment is not drastically affected. So here we can see that the ancient and modern materials, you can see in the left and in the right, definitely this is the result of the new materials development as well as the new process development. So this has led together to the technological advancement, and definitely and the drivers for such a change are market needs. So economics play an important role in determining whether we want a change or not. So there are so many different uh, parameters which determine what should be done to satisfy the market need and bring a new product or some adapted product which can be satisfying to the customer. Okay, with this, I would say that we already have so many different materials, which we can say that this is a taxonomy of materials, because in databases, as already has been said, that there are different softwares available for material selection and process selection. So there is a hierarchical way of material database arrangement, and this is how it is. We all the materials, ceramic, glasses, metals, polymers, elastomers, hybrids. So you can see the family of material, then different in one family, then different classes of material, and one class of material, this is subclasses, and the subclasses, different members, and last member, if you choose, this has different attributes like density, mechanical properties, thermal properties, all these properties are available. So these databases are available for in the form of hard copies as well as digital form. And similarly, you have the data available in the form of same process, same arrangements. In for processes, for example, you have different processes like joining, shaping, finishing, and then in shaping, for example, there is subclass, classes of casting, deformation, composites, powder, and prototyping. And in molding, you can have different subclasses like this. And for injection molding, you can find the data in the form of this. What kind of material can be processed to injection molding? What shape can be made? What could be the size range for such processes? What is the tolerance level we can get in these processes? All this data. So all this data you may require when you go to material selection and the process selections. So now, what? So if we have an idea to make a product, then how the material databases can be used? First of all, the available databases can be selected from for the application, what for the product we want to make. And so we can use the databases and we can use the available softwares. Available softwares will always have the databases available throughout the world. And then the other is the find an alternative better material for a conventional application based on novel process. You know the material what I'm using, and this is what we want to use. But since there is a new process, and new process can give rise to better properties also, so you take the material for processing by a new process. Now the third possibility is that you discovered a totally new material overall. You have an application in mind, but you do not find any material. So what you do? So if you wait for the normal course of action for discovery of a material, it is more than 40-50 years. So that is not desirable. So you discover a new material for projected application based on some new techniques like high throughput experiments, where you do a large number of small experiments to reach to the conclusion by making small samples of materials to decide on the properties available for different compositions. Then you can use simulations where molecular dynamics, density functional theorem, all modeling processes that can be used to have the fundamental properties of the materials. And then you can use new technologies like machine learning, artificial intelligence, neural networks, which is based on the data available with us. How many data is available and people are trying to spare, that is a different issue altogether. But these techniques, if applied in a proper consortium throughout the world, can lead to discovery of new materials in a very short span of time. So how we do this? So if we want to make and design a material, then there are 4 things we should take care of: the process, microstructure, property, and performance. So we can go in 2 ways. We start with the process and go to the performance, or we know what we want and then go back to the process, that what we can do to get these properties. So we have the correlation between properties and performance. We have the correlation between microstructure and properties, and we have a correlation between process and microstructure. So they define the rules. These intersections, they give the rules, and this is why if we want to discover a new material, we can go by Addisonian method, trial and error, use a process, see the microstructure and see the properties, and finally see the performance. So this is a cause and effect process. And the other process is, and this process takes time. Other processes, you have the application in mind, you know what are the performing parameters, and then based on these rules, which we can say this is a science-based methodology, using these rules, working on the databases, and you can define the goals and means here, and can go back and do the statistical analysis to reach to given material and process. So here this is the prediction, and this is the optimization of optimization and design of new materials. What are the platforms where we can do that? We definitely understand that we have computational tools. We can have extensive digital data and definitely experimental tools. And right now, in the first paradigm of, can somebody please mute the, yeah, okay. In the first paradigm, we depended on empirical sciences, where we did whatever we want doing experiments. Then we ended up with in the second paradigm, where we came to new laws of thermodynamics, and then we made some models, and experiments were supported by these thermodynamic laws. And then in the third paradigm, we started doing computational predictions using simulations and modeling, and those techniques used to have required very strong computational facilities, and process was slow then. But today we are running into fourth paradigm of data-driven science, where we want more and more data to statistically analyze and predict what could be new materials and processes that can be applied. And onto that, we are now in the going to modern manufacturing era, where actually earlier we used to do mass production, where the cost as well as the customization of the material was low. Customization means according to our choice. So initially in mass production, we did not get the product according to our choice, but the price was low. If we want to have a product according to our choice, then the price increased. But today, with the advent of additive manufacturing and other processes, people are trying to respond to the requirement of mass customization, where you can produce the materials which whatever we want, but at the same time, price will be low. So this is where we are tending to in the days to come. And these are supported by different techniques where you have additive manufacturing, you have new industrial revolution, you are getting Internet of Things within the industries, and there are advanced robotics. We call them cobots, that are collaborative robots. So here you can see additive manufacturing is a process, then the predictive capabilities from artificial intelligence, machine learning, and neural networks, where they help us in decision making, monitoring the process based on sensors and actuators, and they do process optimization for us. And definitely robotics is going to play an important role in the manufacturing processes. So, but though we had been working in these processes and material selection based on the conventional techniques, and those conventional techniques are, we think of raw materials, process and structure, and we did not care that what is the effect of processing a raw material to get a structure on the environment, society and economics. But today it's very important that we must take what is happening to the environment, what is happening to the society, and what is happening to the economic situation of the society. And these are the sustainable needs, and these basically give rise to environmentally benign products. So what we came to the conclusion that we must do one thing, that we have to select, we have to discover new material and processes, but at the same time, we have to be very benign on the environment. So these things have to be taken care of in selecting and processing materials. Now with this, we come to material selection now. And before going to material selection process, we must say that what is the need and how the material selection process is driven by. So any drivers for materials and process are, we already came to know that there are many new materials available and continuously new materials are being developed and of different kinds. For example, earlier a kettle was made of cast iron, now it is plastic. This had to be conductive because to heat the tea inside, now the coil is inside, so you don't require it to be conductive. Similarly, so what is the difference? There is a change in the idea, and that idea came to manifestation in the form of a plastic kettle. And what is the role of materials here? It is very easily visible here. Similarly, for bulbs, from incandescent bulbs, so LEDs we are there. We started from this, we came to this, and now we are here. So it all depends upon the requirement and the possibilities. New materials, new material types, there are new manufacturing methods available, and the properties of the materials which are already existing has been improved by continuous research, or there are new uses, increased uses of advanced materials. So all these are the There is a competition in materials. There are new design configurations feasible. Means you have a product now. You see that okay, aesthetically we have to make a new configurational design of this. Then you may require a new material for that. So definitely you will search for that. So overall, we can say due to rapid development in materials technology, material selection is both critical and complex. But how to do that and why to do that? So material selection is the big question before the people. And here you can see why to select a material. First of all, to make full use of the possibility with engineering materials. Second is to avoid unnecessarily extensive structures. That means we can have titanium in place of steel, mild steel, for example, but that may be very costly. So we have to be very careful that what is the most economical material we are going to choose for. And obviously we have to take care of strength, load bearing capacity, so avoid failures. So we have to do that. To respond to environmental regulation, definitely, as I discussed earlier, that now all the governments in the world, they now know that we have to save our environment. We cannot leave it unregulated. So we have to respond to those regulations and to increase the reusability of materials. And when to do it? Why to do that is that we know. When to do it that we want to make a new product. We went to the market and saw that the customers or people, they want a new product for to replace something. That is the main driver for the designers. Or a product is modified and redesigned, then again we will have to have a new materials, or any product or component is failing. In that case, we should have a new material and process selection. And who will do that? Definitely design engineers in collaboration with materials engineer. Okay, so what is design? Means if we want to make a product, definitely we have to make a design. And what does material do in a product design? So if we define the design of a product, then we can say that design is the process to translate an idea or a market need. Obviously, idea is coming from the market need. You do market survey, and we come to know that something is required for the market for better economic growth of the company. And then with that idea we start, and you finally go to embody the idea into some kind of prototype, and finally product to be manufactured using materials and processes. And then the stages in design to manufacture require selecting materials of which the product is to be made. And it also requires feasible and cost-effective process for making it. Okay, the choice of material cannot be made independently of the choice of process. That means if we choose a material, we may say that ceramics have very high strength, but we cannot roll it, or we cannot process ceramics in some different way the way we do it for metals. So we have to say that what material and what process, they have to go hand in hand, and very carefully we have to choose. Although material choice is dictated by the design, but sometimes design is such that you cannot have the materials available. And that in that case, you have to discover a new material for a new application altogether. And if we look at the cost of this product development, then we can say here that this is the x-axis, which says the conceptual design. If we want to do, then conceptually the technical knowledge is very low in this case here. Technical knowledge is low and the cost is very low. The technical knowledge, sorry, is very high, in this conceptually, but cost wise, we do not put lot of cost in that. But with time, when you make a detailed design and develop, further the technical knowledge increases and cost also increases. But once you have reached to a system use, then here the knowledge and cost and the total is coming here. So what we want to do is in the design phase of product, we must reduce the knowledge gap. This is a knowledge gap. So knowledge gap has to be reduced, and then you can basically lead to a full-blown product design and use. So technical knowledge and the cost is very important. So we have to stick to the knowledge in the first phase, and then if we feel that knowledge is not enough, we should go back and do the things so that without incurring large amount of cost, we fill the knowledge gap first and then go to any construction or production. So this is very important thing to do. And for all the material selection processes, we need to consider the following. That is product shape, what shape we want to make, what should be the mechanical properties of the component or the product, or what are the physical and chemical properties like specific gravity, thermal coefficient, expansion coefficient, corrosion resistance, and all those things. And obviously, if it is load-bearing material, then we have to have very careful about microstructures. And then once you choose the material, then what is the processing consideration? Whether it is castable, can we form them easily? Is it machinable, weldable, and all those things? Obviously, the aesthetics and environmental impact again, and then cost and availability of the materials. So what should be the strategies for the materials and process material selection? Here, generally, we have one input and a transfer function and output. So this is a selection strategy. This determines that what would be the output. So design requirements means and features of a product means what it is going to do, what would be the function of the materials, and these design requirements are basically determined by the market need and our own exercise of determining in the product what are different components and what different components are going to function, and then they will decide that how the product will perform. So this is totally intangible thing, and then you apply some selection strategy and reach to the selected materials and processes. The first strategy is measured attributes. So in design requirements, so design requirements, you put the numbers that, okay, we want this much strength, this much modulus, this much corrosion resistance, this much temperature bearing capacity. So all these things, measure attributes. This is very scientific way of doing it, and you end up with we end up using a strategy, this strategy, to innovative possibilities, and you have freedom of choice. Why? Because in this process, you are not dealing with people, you are dealing with the numbers and databases. So this is most preferred way of preferred strategy to do, and we will basically in ongoing other slides, I will consider this as the more. Then second strategy is expert opinion. So obviously, if there is an expert, he will have limited knowledge, and you will work with this limited knowledge, and then also this expert will give you answer to some questions, and these questions will return to you as an output only a known solution. So experts will have only known solutions, and they can guide you through. They may guide you to go to strategy 1 also, but the output, the innovation possibilities here is very less compared to strategy 1. And then strategy 3, here also we want to have the expertise from other people, but this is not the mental support from the expert, but from the previous application. So you don't go to expert for the basis of his mental understanding. You just go by the fact that for such an application we had used this material and process, so we will use the same. So returns cases with features like that of the present problem. So same problem and same solution. So strategy 3 is highly non-scientific, but may work. So what is the design process? So if design requirements are known, that you go to market and know what you require, and then you conceptualize the product, then there is what the product would embody, and then what would be the details of the product. All those things give rise to product specification. So up to now we are not in production, we are in design process, and what we do is initially once we know what we require, so we know what the function of the material is, what would be geometrical constraints for this, or what would be the geometrical constraints or material constraints, and what would the working principles of product means, what different components in a product, how they are going to function, and then you evaluate your concept based on the requirement of the market. And once you do that, then that concept has to be translated to a case where whole embodiment of the product can be defined, like what is the layout, what is the scale of the product, means size, and what kind of product would be. Then you will model and analyze the assembly. If you have different components, then what will do? You will use some modeling platform or analysis platform to try to assemble different components and see how it looks like and what would be the specification for this. And then you evaluate that. And after that, once you know the embodiment of the product, then you start analyzing it. Then you basically in detail 1, you choose a material and process based on the embodied structures, layouts, assemblies, and all those things. And finally, you get product specification. And if you are not able to satisfy yourself with this product specification in the market, then again you go back to the concept and again come back like this. And here the same thing, you have to define function, and for that function, material will decide what function has to be performed, and then shape and process has to be determined, which are interrelated in nature. Now, just an example of a concept to details, how the concept, embodiment, and other details are formed. There is an example for this. Here you see there is a wine bottle, and this had to be transferred to a glass, and the customer wants that very easily we can transfer this. There is a cork inside and close. Now, there are several possibilities how we can do that. We can pull it, we can shear it here at this at the periphery. This cork can come out, or we can push it from inside, or we can just drill it, or we can break it. These are the possibilities. But how many possibilities of this we can choose to? So resort to break it, to drill it, because this may be contaminated later on, or we cannot resort to this also. So these two options are out. Now the concept is you have drill here, and once you put it, then you can take it out, or you can have knives here and then do this thing, or you can pressurize inside and this will go out. So these are the possibilities. Pulling, shearing, and pushing are there. So this is the concept now, and that concept can be translated in so many forms. So you have to decide these forms, and obviously, what would be the mechanism of using this concept to this has to be decided in the conceptual process, and then once you do that, then this product has to be defined in detail. That is, what is the material, what is the material and how they are going to produce, what would be dimensions. So these are the embodiments of the product. Once you decide all these things, then you go to a product manufacturing. And for doing all these things, you have design tools as well as materials data. So design tools means function modeling. Once you know the function, then definitely you can model it, what the material has to do. Then viability studies you can do. Geometric modeling means how to assemble and see the things in perspective. You can have simulation methods applied to this. You can have material selector softwares. You can have component modeling. FEM analysis you can do to reach to some conclusion based on your ideas. Then design for manufacturing and design for assembly softwares you can use to reach to product specification from the design requirements. And you always will have materials data for all these steps of the development. So once you decide on the function, service condition of the product and the cost of the product, then like this, and then you need to choose the materials and the processes. So in choosing the materials, again, you have to consider the properties of the materials available, then availability of the material, the easy availability of the material, and how costly it will be to process it. It will be, and then you choose the respective processing methods. So you will have to choose equipment by which you can do, whether you want to do casting, you want to use powder metallurgy, or you want to do additive manufacturing, or so many options will be there with you. And all these options, processes will be giving you the data on different parameters. I will come to that later. And the interrelations of design, materials, and processing to produce a product is very important to understand. Professor MFSB, he collected a lot of data and tried to correlate them to put in proper perspectives. And this is the chart for different classes of materials, for metals, polymers, ceramics, and hybrid materials, as I talked in the second or third slides. And then for different materials, what is the maximum temperature of service is possible. This can be found. Similarly, you can find Young's modulus of different materials, or you can find the prices, relative prices, basically prices of different materials for different class of materials, basically. So I am showing only 3 of the charts, but the large number of such charts are available for a designer or a selector to choose from. And these are the charts, but today these charts have been already put in softwares, so mostly we do not go to these charts now, but all these softwares use these data to for selection process. So what are the different stages of a selection process? Now we for materials as well as processes. So we have just say we have the databases for all materials and processes. So material properties and process limitations, processing routes, tolerances, finish, size, everything. All the data we have, and now we know the design of my product, and I want to choose the final material and process for making that product. So I have several questions in mind. So what I do then is, first of all, I resort to screening. Screening means what screening we should do. So we know that what our product would be doing. So function and we have defined. We have to put some constraints. For example, we have a large amount of materials, but we say that, okay, we want a material for which the Young's modulus should be more than 100 GPa. So that becomes a non-negotiable condition, and that is a constant. So any material which is having modulus less than that will be screened out. So we have to put some non-negotiable and negotiable constraints. Negotiable constraint means if we have is a desired constraints, and desired constraint means if we have it, it is very good, but if it is not, then also we can choose that material. Then you have to have an objective. For example, you want to have a maximum load bearing product, or you want to have minimum mass component, something like that. So the objective has to be maximized or minimized. You have to have a reduction in cost, minimum cost you want, minimum mass you want, minimum or maximum strength you want. So based on those things, you set the objective in screening. So all those materials which do not fit to those function constraints, then those constraints, they will be out, screened out. So what are the different processes by which we screen? Here material screening methods are there, but so many methods are there, but I will not be going in detail of this. I will take only this one, chart method, to show you that how it is done. Though we do it in softwares, using softwares, but softwares also use the similar techniques for screening the materials. So chart methods are there, and now new methods of artificial intelligence methods are available where computational material selection systems are developed. Those things need to be set out. And screening methods are basically applied to charts made by Professor MFSB, and these are tested and tried. And these material selection charts are available for preliminary screening of materials. I'll come to that what charts are. And then the method is easy to apply when the design of the component consists of a single objective. That means we want to have an objective of minimum mass criteria for designing the product. Or if we have minimum mass as well as maximum strength, then we have multiple objective criteria that we will not discuss today. But you can go through book by Professor MFSB and you can find it all. This is a SB chart where you can see all the materials classes are plotted here in their strength and density. And here, this is very important. These are basically the objective, the material indices. I will try to let you know what these indices are. So here you can say that this is the one index of material where the yield strength and density is concerned. This is guideline for minimum mass design. If similarly, you have Young's modulus, relative cost per unit volume of the material. For that, you have a chart. For Young's modulus and density, you have a chart. So if you go to the book, you will find that large number of such charts are available. And these charts have already been transferred to softwares and material selectors. And the principles what I am going to talk about, those principles are basically used to select the material. So here what we do is generally, sorry, this is not correct. So here this is just to let you know how to process. So just say you want to have different functions. You can have a tie rod where a force F, sorry, where force F has to be borne by this tie rod, or there is a beam where force F can be applied, or shaft top T has to be borne by this. So different applications you can have. So for example, if you have this beam and you want to have this beam with stiffness specified, means with the load, the deflection is minimal. So this is stiffness is specified. This is the constraint for designing this beam, and your objective is to minimize mass. So you have to choose material which can reduce the dimensions of this, because density is fixed, for example, the dimensions of this, and so if length is fixed, you have to reduce the cross section so that mass will minimize. So material index is this. This is the material index. So rho by modulus half. If this is, we have to minimize this, or we have to maximize E half by rho. So this is the index. So how to do it? Let us see. This is a tie rod. You have to apply a force here and design for a strong tie. We want to have a strong tie rod with minimum mass. So constraint is that load and length is specified. So we know what much load is required to be sustained and what is the length of this. Now our objective is to reduce the mass to a minimum, and variables are only cross-sectional area and the material. So mass of this will be area into length, that is volume, into the density, and we have to it has to withstand a load of F. So the strength of the material should be more than F by A. So mass will be F, L, and rho by sigma F. This is what we end up with this expression with. So here, this is force F. This is the functional constraints that force F has to be sustained by this. Length is a geometrical constraints. So length has to be this, and this is the material constraint. Okay. So if rho by sigma F has to be minimum for mass to be minimum, so we have to maximize it for M to be minimum. Maximize the inverse of this. Okay, so this is how we go for. I will come to that later. How to use this to select a material. Similarly, for a beam like this, what based on the stiffness, so we define the stiffness. This is the force we have to sustain. That is load lead to a stiff material, and then length is specified. Mass has to be minimized. We have to choose from the sectional area, cross-sectional area, and the material. So what we do, stiffness is F by delta. Delta is the deflection here, and that should be more than this. This is the length. This is second area of movement. and this is the modulus, and this is the constraint. It depends upon how the load is distributed on the material. And once we do all these things, then we end up with the expression for mass, which should be equal to or more than this. Here, length is fixed, S is fixed. These are the constraints. So again, functional constraints. These are the geometrical constraints. This is material constraints. So inverse of this has to be maximized. So how
Dr.
to,
Srivastava?
yeah.
This is Aniket. Sir, sorry for interruption. It is just for a gentle reminder for 1 hour.
Yeah, so I have 1 hour 15 minutes, no?
Yes, sir.
Okay, no problem. Yeah. So now, how to do this? So in this graph, we are designing it for tie rod, so strength and density. So this is the slope. So just say sigma f by rho. If you want to make a slope of this constant C1, we take a log, and then this would be a line where the slope is 1 and between log of sigma f and log of sigma and log of rho. So this line, this shows that here the parameter of the metal index is has some value. Now, if you see that if that value increases, what happens? We are moving in this direction. So sigma f by rho, we are increasing. That means yield strength of the material we are increasing in this direction. So if we want to have a material for us for sigma f by rho having some value here, and then we end up with these different materials for our applications from the database. Okay. Now, at the same time, if we want that our material should have a strength of more than 600 megapascal, then this material is gone. This will not be available to us, this area. Okay, so any material which shows strength above this and any material which is having sigma rho by f more than this, that means this area will be chosen. So you will have this only available material. So this is how you screen a material for from these charts. So what I was talking here is the principle on which this data is dealt with in software also. Okay. And the second thing, what you can do is you can have, for example, for minimum cost design. How to do minimum cost design? So cost of the same material, cost of the material will be mass into cost of the material. That is cost of material will be added to this here to the mass. All the other conditions are same. So index will be the material index will be sigma f by cost of material rho. So what we define here is the relative cost per unit volume. This one. So here CM rho is divided by cost of mild steel per kg into density of mild steel. So this becomes relative to mild steel. And then we plot CF by CVR here in this fashion again and try to find out as this increases the cost here, the cost is high. Cost is high, then mass index will be low. So we want to design materials where the cost per unit volume is low. Okay, and if this is low, so this will be high, and then we move to this direction. And there we can choose material which can give us a better low cost as well as minimum mass. So these are the application of the charts for design. Now I go to material shape combination selection. Here just want to let you know that different shapes will have different second moment of area about a given axis, for example, and this is a section area. So in this case, what we define is this is the value where sigma BE, which we call a shape factor. For example, if the shape factor is high, then your material will be very good in bending. Okay, like that. So if you have a sheet, it will bend, and as this value increases, like I section, then this will be better. And this is superimposed with the data from steels, timber, or aluminum alloys, aluminum extrusions to show that for different materials, what kind of relationship is available in the data for second moment of area and section area. So here what we would like to emphasize is if we want to design certain component for a given shape or certain material, then what shape we need to choose based on that. So here it will be shape factor. So modulus we have here, this is a density. Different materials have different modulus, and what we do is we put a, for example, this is steel. We put a constraint of modulus that is called stiffness constant EI, like this. So take a line here parallel to this, and these are different lines showing the value of EI. Okay, and at this point when you come, now you see here second moment of area, here second moment of area, and so this goes down to this and choose a value for 10. Okay, for aluminum alloy, and then sees here at where it is cutting this material at this point. So here there is section area and there is density. That means if we are going in this direction from 1, 3, 10 like that, then higher this, lower this value, then our material will be more small in mass. Okay, so for the steels, we choose go to this, define EI, and then we use the shape factor for this, and then using this shape, we choose to choose this shape factor. You see, the S is the value of what we are getting from here. EI is shape dependent, and this is shape dependent. S0 is for a square, and S is for a given shape, and then when we reach to this value, that means this is specifically for a given shape. Okay, and then for that shape, we are going to have this value. Similarly, if we use aluminum alloy, then for the same value of EI for the same shape, go to aluminum alloy and see what is the section area we require for this. Okay, and then you choose soft wood, use the same EI, the same shape, and then go to this timber and then to say what is section area. So here we find that aluminum has the lowest value. So the performance of this shape as well as the material can be decided by doing this exercise and looking at what material will with this shape constraint can be chosen for the minimum mass design. So with this, I move to the next one. So materials and process selection stage. And here again is screening. I talk to you, and once we do the screening from the data, then you get a subset of materials and process, and this subset can be ranked. Means now from those subset data, you see the objective and to develop an index for ranking. As I showed the material index. Similarly, we have process indexes also, and based on those, we rank different materials and processes for our application. Once we rank them, then again we end up with some kind of subset of materials and processes. And then once we choose in this, then we go for supporting information. Means we go to local expertise, then case studies, we read, go to journals and databases, and again confirm that the material we are choosing, whether it is okay or not based on the previous experiences. And similarly for processes also, we go for the local expertise. We see whether we have the equipment and tooling and what is the cost of this tooling, whether we should be able to use it or not, on literature data. Once we do that, then we can confirm that, okay, this is the material and processes we want to use for our product. And there are process information maps for selecting processes. And again, what I'm talking about is process information maps are available, but now they are there in digital form, and they contain the data like what is the process, shape, cost, mass, tolerances, section sizes, etc., etc. Then what are different process variations possible? What are different materials that can be processed using that process? What are the economic factors? I'm talking about the data which is available in process maps for a given process. Typical application of a process means what are the examples of parts commonly made with this process? So you will have an idea that, okay, I want to make this part, and this process has already been proven for making such parts, so we can use that. Then design aspects, what is the shape complexity, what is size range of the material you can use. For example, a very large casting size cannot be made by investment casting. So those differences you can see here. And then quality issues, what are the surface finish and other things available with this. So using these process metrics, we have different matrices for process, material, shape. It is available in the books. And here for different shapes, different processes are there. Then you can get here what are the shapes possible with which process, like that. And in this case, it is very important to understand that the total cost associated with manufacturing for a product, mainly if you produce very small number of pieces, then the tooling cost is very high. But as we increase the number of pieces production, then the tooling cost basically is compensated with the profit received in the producing large number of pieces. And example is that here for this connecting rod, making a connecting rod, if you see there are different processes, investment casting is very costly, then die casting, then sand casting, but forging is initially it is very costly to produce very small number of pieces, but it is very cheap if you are going to produce large number of pieces. So we do have process maps like this here, just to make it more visible. See on the top, this is the material, and for different materials, you have data sets, and then what is the quantity you can make of these materials. This is available with the softwares. And then for magnesium alloys, for example, this shows like this. 1.6, 1.7 like that for different uh, number of pieces, and these 1.6, 1.7 are like this. Casting processes, different casting processes like that. Different plastic forming processes. So processes are given here inside these squares. So for a given material, for a given, for example here, for a copper alloy, for example, if you want to have 10,000 to 1 lakh number of components, then these are the processes suitable for this. And these are basically 1.2, 1.4, 1.9. So here you can see the sand casting, pressure die casting, and space casting. They are the suitable processes for making copper alloys with this main number of products. Similarly, for any stainless steel, for very high number of products, then you can have rolling, drawing, automatic machining, and space casting like that. So these are the data sets available with us, and these can be used for selecting different processes and materials. And computer aided material selection is a I have already talked to you on this point. Here you have to give the constraints, for example, modulus, density, price, minimum, maximum temperature of application, thermal expansion coefficient, what would be the, and there are n number of such data points you can enter to restrict, to screen the materials from the given databases. For example, in this case, if you put modulus of 50, then here all the materials which are below this limit, they are gone. Okay. So similarly here, if you have metal price, just example, metal price you fix, then all the material which is higher than this price will not be selected, and you will be searching in this region. Similarly, if you fix, as I told you, this number for a beam, then you fix this line and then say all these materials below this line, they are out of screening. They will not be screened. They will be screened out basically, and you will have options of these materials only. Okay, so you can have multiple number of constraints, and your software will give rise, bring to you a number of materials and processes for you to select between, and then among them you can base your selection based on the previous experiences and the literature, as I discussed earlier. And to summarize all these things, we can say that efficient materials and process selection can be achieved by intelligent scrutiny of reliable datasets on existing materials and process attributes. An integrated approach of experimentation and computation or simulation is a need of the hour for efficient materials design. And big data science has been globally recognized as a new paradigm for materials discovery, reducing the span of translation of materials from laboratory to market. With this, I thank all. Thanks a lot for your patience hearing. Thank you.